Hi, welcome everyone. We'll get started in just a few seconds. Okay, welcome everyone to today's quick Quake briefing on the magnitude 7 Alaska Hubbard Glacier earthquake hosted by the EERI Northern California Chapter. I'm Maggie Ortiz-Milan, the Director of Programs at EERI, and before we get started, I just want to take a few moments to share a little bit more about EERI for those who might not be familiar with our work. The Earthquake Engineering Research Institute is the leading nonprofit organization that connects multidisciplinary professionals dedicated to advancing earthquake resilience in the U.S. and globally. Our members include researchers, practitioners, and students in engineering, geoscience, social science, architecture, planning, emergency management, and community leadership and advocacy. If you're not an EERI member, I encourage you to visit eeri.org to learn more and consider joining. EERI hosts regular webinars on a range of topics, including reconnaissance findings from the Learning from Earthquakes program, featured content from our journal Earthquake Spectra, and quick briefings like these. Recordings of all of our webinars are posted on the EERI YouTube channel. We'd like to thank FEMA for the support that they provide to make webinars like this possible. And EERI's work wouldn't be possible without our subscribing member organizations and partners. We would like to extend a special thanks to Computers and Structures, Inc., CSI, for their generous support as our top-tier visionary member. The commitment of CSI and other high-tier subscribing members like Degenkolb, the California Earthquake Authority, and Kinemetrics make EERI's work possible. Thanks also to our silver, government, and bronze subscribing members. If you or your company is interested in learning more about the benefits of EERI subscribing membership, please contact EERI at eeri.org. Now I'll turn it over to Dick McCarthy, President of the Northern California Regional Chapter, to say a few words about the chapter.
Well, welcome, everyone. And I would build a little bit of what Maggie just said. The Northern California chapter is very active. We have great experts and we have great student chapters. And what makes us a little bit unique is we also are very active at the Capitol here in Sacramento. We've had a very active year so far and expect to be even more active as we go towards the summer. So with that, I'm going to introduce Bruce. Would you please introduce our speakers?
Okay, great. Thank you very much, Richard. I want to welcome everyone to our briefing on the magnitude 7 earthquake that struck Alaska in December. My name is Bruce Mason. I am one of the executive board members for the Northern California chapter, and I'll be serving as your moderator today. This is the 5th year of our briefing program, and this is the first briefing in 2026. Now, our quick Quake briefings are free to everyone to view. So in other words, if you're a member of EERI, you'll receive email notifications, and then you'll also see our announcements in the Pulse newsletter. And if you're not a member, you can get on our mailing list. And how you do that is you would send an email message to me to the address shown on this slide. Now you can view our briefings live like we're doing today, or you can see them on the YouTube channel. So if you go to the YouTube channel and just type in Quick Quake Briefings, a list will come in. Now on to today's briefing. On December 6th, a magnitude 7 earthquake occurred at 12 noon in Alaska near the Yukon Territory border. This is the largest earthquake to occur onshore in Alaska since the magnitude 7.1 Anchorage earthquake in 2018. The current earthquake occurred underneath the Hubbard Glacier in a very remote area. It's sparsely populated, thus there was no damage to the built environment. However, it triggered over 700 landslides and avalanches. Some were spectacular, having travel distances over 3 miles. We are excited to have 2 speakers joining us today. The first one is a seismologist that's joining us from Fairbanks, Alaska, and he will explain the seismology of this earthquake. Our second speaker is a research geophysicist joining us from Golden, Colorado, and she will explain the landslides and avalanches that were observed. The format of today's meeting is this. It's a 60-minute program. Each of our speakers will talk for about 20 minutes each. Then the remainder of our time will be for question and answer. And we encourage questions from the audience. And how you will do that is you will hit the Q&A button that you see at the bottom of your screen. You'll type in your question, and then behind the scenes, another one of our executive board members, Donald Wells, will compile these questions, and he will come back later in our program and pose the questions to our speakers. Now, we recognize there might be more questions than time, so each of our speakers has kindly put their email address in their presentation, so you can be able to email them directly. And then in the coming days, they will try to answer your questions. Now, what I'd like to do is introduce our first speaker, Dr. Michael West. He is the Alaska State Seismologist. He's also the director of the Alaska Earthquake Center. So, Mike, can you please proceed?
All right, good afternoon. Let me share my screen here and just a confirmation that you've got a full title slide in front of you.
Looks good.
Great. Hey, good afternoon, everyone. I appreciate the opportunity. I'm going to spend the next few minutes here showing a fair amount of past historical work, as well as to set up this earthquake, and also things that are ongoing from a number of colleagues that I've listed here, but really a whole bunch of people that I'm probably selling short in my title slide. I hope my credits along the way make up for it. I was told really early on in public speaking that you should try to meet your audience where they are. So I'd like to begin this presentation, if I can find the right buttons. I'd like to begin in California. If we look at the plate boundary of North America with the Pacific Plate, we have the San Andreas Fault, surely well known to everyone within this particular audience, but just a reminder that the San Andreas system exists because, on a big scale, the Pacific Plate is moving northward past North America, creating right lateral motion on the fault system. And that process is bigger than California. It extends, way down through Central America. Things get a little complicated in the Pacific Northwest with the inclusion of the Juan de Fuca subduction zone, but it's still the same essential plate boundary. Now, if we continue that system on up north, what we find is that same basic transform, that translational motion is occurring. Do you see a mouse? Do you see my mouse or not?
Actually, no. Try moving it. I don't see it.
That's probably okay. I'll just be aware of it. That's fine. Here at the north end, off of British Columbia and southeast Alaska, we have the same basic motion that you see down on the San Andreas as the Pacific Plate moves inexorably northward. If we move a little further west, south of Alaska and into the Aleutians, North America and the Pacific Plate are colliding directly. And so we have the subduction zone, the resulting subduction zone, and the whole arc of the Aleutian Islands. But that presents a challenge in the corner where these two huge, global scale systems intersect, where the subduction zone and the transform come together. In this area up here, I probably shouldn't refer to it as the armpit of Alaska. It's a magnificent, beautiful place, but I will for a moment. That's a really complicated tectonic place that has been the subject of attention for many, many decades and continues to hold a lot of puzzles. So let's zoom in on this area, kind of get oriented in this slide here. Down in the lower right, we have that fault system, which we refer to as here on the northern end as the Fairweather Fault.
Okay, Mike.
Yes.
Bruce Space for. I see the audience can see your cursor. If you want to use it, go ahead. I don't see it on my screen. Please continue. I'm sorry.
All right. I'll use a cursor. I won't rely on it. But the Fairweather Fault System coming up the coast here and reaching Alaska and the subduction zone over here. There's another complicating factor in this mix, and it is this awkward block of oceanic crust here, which we refer to as the Yakutat block or the Yakutat terrain. It's 50, 100 million year old, thick oceanic plateau crust. So it's thick, it's buoyant. Basically, it doesn't want to subduct. And it's gumming up the works of the subduction process here, essentially colliding into North America and causing all sorts of downstream impacts. The big thing that we consider it to be responsible for is driving, you see these three-dimensional arrows from this paper in 2003, kind of driving this westward motion, or you can even think of it as sort of a counterclockwise rotation of southern Alaska along a whole bunch of fault systems that arc across the region. Many on the call may remember the Denali Fault earthquake in 2002, the magnitude 7.9 earthquake. This is a paper, this particular figure is from a paper explaining the Denali Fault earthquake. It was a result of this counterclockwise, translational motion. So, and again, this Yakutat block is considered a primary driver of all of that. One notable, or often cited paper title from 2001, Stephen Johnston referred to this Yakutat terrain as just the latest instance of the Great Alaskan Terrain Wreck occurring in this area. But the point is, it's a messy place. This is a really neat figure from Julie Elliott and Jeff Freimuller a few years ago. If you break southern Alaska into little tectonic blocks, and then you model the motion on each one of those, these arrows represent the horizontal motion of them. And again, it's just a nice indicator. It shows this tectonic rotation that we see in southern Alaska. So, all of this is kind of a long buildup, but where it leaves us, back to this figure, is we have our huge transform boundary coming up the west coast and kind of dead ending up here somewhere in a set of splay faults and complicated situations in southern Alaska. And then we have all of these sort of east-westish strike slip systems that accommodate this rotation. And there's a problem in that they're not connected. Somehow motion from one needs to get to the other. So for many, many years, people have inferred the existence of some sort of a connector, a connection that would allow these two fault systems to communicate, if you will, with one another. And there is good evidence for this. If we return to that same geodetic paper I showed a moment ago, Elliott and Freimuller, we're zooming in on the left here on this little area, the area we were just looking at. This dotted line, this dotted blue line demonstrates that on one side we see very strong, fast plate motions, and on the other side we don't. Well, the way you accommodate that is with a fault of some sort. But it's remained relatively elusive. If you look at historical seismicity, this is a paper from a couple of years ago, you can maybe make an argument that there's some historical seismicity that might map out a connector, but I think it's fairly weak. 2 years ago, when the U.S. Geological Survey completed the latest update to the seismic hazard map for Alaska, this was the first update to the seismic hazard map in almost 2 decades. This image here, published in EERI Spectra, I would point out, is the fault set that was used in the development of that model. And I put this up to illustrate that Though it lacks geologic evidence, the need for this connector fault, some sort of connection between these, the evidence was strong enough that it was included in this effort to produce the hazard map. So all of this is rationale for why on December 6th, when this particular magnitude 7 earthquake happened, it was of considerable tectonic interest. It became a really important piece in this larger puzzle. So let's go back to this figure yet again. We have our little connector, our inferred connector here, and the location of the earthquake on December 6th fell right in line with this. And if you are not familiar with these beach ball images, it's just a way of representing the motion on the fault. Basically, it was strike slip with this orientation here. Pretty much exactly what one would expect on a fault system connecting these two blocks. So seems pretty darn clear that this earthquake helps fill that gap, if you will, in explaining this connector. All right, here's a 24-hour seismogram, 12 hours before the December 6th earthquake and 12 hours after, and it's a great illustration of just the vigorous aftershock activity that is not, I mean, it's certainly expected for an earthquake of this size. We do find that these large crustal earthquakes, like the Denali Fault earthquake and this one, are particularly prodigious in their production of aftershocks. And that is what we have seen this time too. So we have thousands of aftershocks, including in the past hour. You know, here we are in the beginning of February. But, you know, these have caused, you know, certainly have shaken people in northern British Columbia, southwest Yukon, parts of southeast Alaska. The aftershocks have been part of the story over the last few months. However, they are also scientifically, I mean, each one of those is an additional a little clue or a piece of evidence to use in figuring out this story. So if you take all of those aftershocks and you start to plot them on a map, we are now zoomed in on this, there's a scale on the bottom there of about 50 kilometers for reference. What they start to do, the locations of these aftershocks begin to paint in the fault. So again, we're not surprised by this. It confirms, it goes along with the focal mechanism, but it appears to map out, you know, a fault that strikes in the northwest, southeast sort of direction, in line again with this connector fault. The focal mechanisms shown here for a whole bunch of aftershocks are a little hard to puzzle out in this figure, but I think the point is they back up this strike slip motion, and there also appears to be pretty good evidence for a conjugate fault of some sort, probably with thrust motion. This is a little bit more enigmatic, but not entirely uncommon for crustal fault systems to have more than one plane at work in the main event. So I think this is an area of very active research at the moment. One of the reasons that it's important to figure out, to understand exactly what faults were active in this is as we try and forecast hazard. So what are the, a magnitude 7 is big enough that it changes the stress regime around it and influences the faults, the surrounding faults. So this next figure is very much a work in progress, a first step here, but a lot of colors going on. But what you're really looking at on the left-hand side of this figure is an estimate based on a fault model, a particular fault model of where certain kinds of faults in the area would have been nudged closer to failure and where they might have been nudged away from failure. And there's a bit of nuance in how this is done. But on the left, if you look at all these little planes, on the right, if you look at these different planes, this is an estimate of how the stresses on surrounding fault systems might have been, again, nudged closer or away from failure, depending on whether they're strike slip or thrust. And again, this is very much a working draft, not a conclusion slide, but an example of why or where active research is going now to try and understand the implications, the downstream implications of this earthquake. So I've got one last topic. I'll hit on ground motions a little bit and then pass this over to Kate. There's a lot going on this slide, and you don't need to follow all of this, but this is a reminder that when an earthquake like this happens, we have ground motion records from all of the surrounding areas, and we can use that to begin to map out, to try and estimate the ground motion across the region. Now, we actually don't have instrumental recordings from very close to this earthquake. So we don't have near source recordings for reasons that will become very clear in the slides that I think Kate will show. But the ground motion records across the region, together with estimates from the fault models, we can put together and show in many different ways. But here's an image from the shake map, the product for this particular event. You can see contours on here. I'm going to emphasize estimated, but estimated contours in this particular flavor for peak ground acceleration, giving us, an understanding for what region experienced shaking at what levels. So I think that's important to keep in mind as we go forward here. And then just one last reminder, it can be hard to keep the ground motions for an earthquake of this size straight. Peak ground acceleration is actually a pretty lousy way for me to be trying to convey the shaking from an earthquake like this. And the only way, forgive a couple of screenshots here, but here's a raw seismogram. This is from a station about 40 miles south of this earthquake. And it's something like 2 minutes of data. But this is the raw vertical ground motion. And what I want you to just to take home from this is the rich set of frequencies that are in this. So as humans, what we actually feel is probably something a little bit closer to this slide on the bottom. We are sensitive to, our bodies feel very strongly rapid shaking, like someone who grabs you by the shoulders and shakes you back and forth. That's motion that we're very attuned to. But when we start to get up into magnitudes that are this large, really a lot of the action is happening at very long periods. The social media posts, people's personal accounts from this earthquake involve the word rolling a lot, or heaving, or there's these long period ground motions. You can see them in the top seismogram. These are waves that take 10 seconds for the ground to go up and down, and they do it over and over and over again. And I just want to end on that note, because as we start talking about ground failure, landslides, avalanches, and things, it's easy in our minds to think about this high frequency shaking that we feel as people, but this cycling of the ground, this long period motion that happens again and again and again, really becomes a much more important factor when we're thinking about maybe not necessarily the damage to my house, but how the side of a mountain collapses. So on that note, I'll wrap up, and just I will leave you with this. If you are hanging out with your California colleagues in the near future and you want to share something cool with them, you can hopefully regale them with the nuances of this earthquake. And I think with some liberty, I think it's fair to tell them that refer to this as the northernmost rupture ever on the greater San Andreas system.
Okay. Okay, Michael, thank you very much for a very informative presentation here.
All right.
I learned a lot about seismology in the Alaska region. Down here, in general, I think many of us are aware of the megathrust faults you have out in the Aleutians, and the strike slip is very different. Something I was not aware of. Okay, what I'd like to do now is move on to our second speaker for today's presentation, and that's a Dr. Kate Allstadt. She is with the United States Geological Survey. She's a research geophysicist dealing with geologic hazards. She specializes in earthquake-induced landslides. Kate, could you please proceed?
Yep, thank you, Bruce. Let me just share my screen. Okay, is that showing the full screen now?
Looks good.
Okay, great. All right, so I'm going to build on what Mike just talked about and talk about the effects of the earthquake. And given that this earthquake was extremely remote and it initiated below a glacier that is hundreds of meters thick, and that glacier originates from Mount Logan, which is the second highest mountain in North America, and this occurred in winter, we're mostly talking about landslides and snow avalanches. Nobody was injured in this earthquake. So much of the material that I'm going to show today builds on kind of a group effort with many collaborators from both the U.S. Geological Survey and the Yukon Geological Survey. At the USGS, we conducted a remote assessment of this event, and then we collaborated with the Yukon Geological Survey, and they conducted a reconnaissance flight and field assessment of this event. And they took the beautiful photos that I'm going to show. But before I talk about what actually happened, since I work with the USGS real-time earthquake products team, I'm going to, of course, first talk about what we actually knew before we knew what happened. And so that's in the minutes to the hours after the earthquake happened. And that is through the real-time products that the USGS produces. So many of you have probably seen earthquake webpage before from the USGS website. So that this screenshot here is showing the webpage for the Hubbard Glacier earthquake. And so when an earthquake happens, and then the National Earthquake Information Center or the Alaska Earthquake Center, or whoever is authoritative in that region, once we get that origin, that actually sets off a chain of models and products that get produced that are kind of interconnected. So once we get the origin, let's see if this will, there we go. Once we get the origin, the location of it, the shake map can start to be produced. So the shake map, and Mike showed that earlier, that is basically a map of shaking estimates. And then that gets improved as we get more information. So as we get information from strong ground motion stations in the area for this event, there were not too many close in, but there were quite a few further out. That gets incorporated when people report what they felt. That also gets incorporated. Of course, not that many people felt this earthquake, so that was not a big constraint for this event. And then really importantly, for very large crustal earthquakes like this one that are shallow, once we get some information about the geometry of the fault, that gets into the shake map. And that's very important for ground failure, as I'll talk about. And so we get that, usually the first estimate is from the finite fault product, which is shown in the lower right. And that's based on inversions of the waveforms onto a plane that is initially chosen based on the origin information and its strike and dip. So it's not based on any known faults necessarily, especially at first. It's just based on kind of projecting that plane out from the origin solution. So that once the shake map is produced and it starts to get updated, it also triggers other products that use that spatial estimate of shaking. And then those also get updated and improved as we get more information. And so one of those you may have heard of is Pager, that estimates economic losses and fatalities. For this event, that was a green alert, and because this was such a remote event. But for this event, the ground failure product actually is very interesting. So that's at the lower left. And so you can see that this overview slide gives a sense that landslides are expected to be significant, but liquefaction was not. And then if we look at what the product looks like, at the lower left, the box here shows that The alert for landslides is orange, which means a significant number of landslides or spatial extent of landslides. So the hazard is high, but the population exposure you could see is almost nothing, which obviously makes sense, and it'll make more sense once I show you the pictures. So this map is just a rough estimate, and it changes as we get more information. And initially the shape map will be for a point source before we know the fault information, and so this can change pretty dramatically once we put the fault in there. And so this is useful, and we use it for many events for making decisions early on before we know what actually happened. So for this event, we used it to decide what imagery or what satellites to task and what imagery to download and what areas to look at in the imagery. And then we also shared it with our partner agencies at the Yukon Geological Survey and also the National Park Service to help them plan their reconnaissance flights, because we didn't have information for the first few days on what actually happened. So before I move on, I'm going to be jumping around to a lot of different maps that aren't all showing the same area. So I just wanted to highlight what I'm going to call 3 different areas, because they'll come up again and again. So the first area is in this upper, kind of the northwest part of the area affected by the earthquake. That's the Mount Logan, which is the 2nd highest mountain in North America. That is the massif kind of around that, and you can see the ground failure product had pretty high probabilities for landslides there. The next one is the massif around Mount King George, and I'll just back up so you can see that the probabilities are high there, but not quite as high for quite as much area as Mount Logan, or this third area, which I'll refer to as the Mount Vancouver massif, which also had pretty elevated probabilities, and that massif is closer to the epicenter. Okay, and then just quickly, so what I showed you there, those are operational earthquake products, and that kind of stops at the models. It doesn't talk about the, what actually happened in terms of earthquake effects. But the reason for this event that we were able to then quickly get information out about what did actually happen based on remote sensing at first and then field reconnaissance second, is that we have this team called the LASER team, which stands for Landslide Assessment, Situational Awareness, and Event Response Research. So over 30 USGS scientists are kind of plugged into this part-time, and it's basically a framework for efficient, rapid landslide event response, and it allows us to quickly spin up a team to respond to any events. And so for this team, it was a pretty small group, and it was focused on remote sensing and communication products. And we produced a web page about the landslides from this event, which I'll share the link to at the end. It wasn't actually until 3 days after the event that we had any information about what actually happened on the ground. And so 3 days later is when we got the first Sentinel-1 image, and Sentinel-1 is a synthetic aperture radar satellite constellation. And and that's called SAR for short. A huge benefit of SAR is that it can see through clouds, and it also works at night because it's an active sensor. And so I was told that at the time the earthquake happened, they were experiencing a blizzard in this area. So it was cloudy for a few days, and you couldn't fly a helicopter. It was also so cold for a while, for about 6 days, that they couldn't actually, like a helicopter couldn't actually fly because it was so cold. So SAR is a great tool to use in situations like this. And this is a particularly spectacular case. And the reason that we kind of decided to do a more in-depth assessment of this event is because one of our remote sensing specialists, Elizabeth Iden, she was just curious, and so she looked at what's called the backscatter from the SAR image. And this GIF here is showing the before and after of that SAR image, and you can see that the white areas those are rougher areas, and the dark areas are smoother. So that's kind of approximately what backscatter shows you. And so she started to look at it, and we were just blown away by how beautifully it showed the footprints of these mass movements. And the reason that they show up so well is because this area is, those flat areas in the middle, that's all glaciers, and they're nice and planar and smooth, and they've just been covered by fresh snow. So any type of mass movement flowing onto them changed the roughness pretty dramatically from what it was before. And so we were able to pretty quickly map the footprints of all these that had the right shape and right context to be some sort of mass movement. The red dots here are mass movements that were at least 2 kilometers long. So they kind of highlight the larger ones. And then the yellow dots have the right shape to be either, you know, a landslide or a snow avalanche. So we're pretty sure that they were real. And then the blue dots are where we saw changes that were harder to interpret. And so the field reconnaissance helped with some of that. But we saw some sort of change happen here, but we don't know what it is because the SAR image doesn't give you color. It doesn't give you anything really except kind of what you're seeing here. So next one. So this map here shows all the points we mapped. So there's over 700 of them. And you can see that they're really concentrated along the fault rupture zone. So this contour here is the estimated 50% G contour. A lot of them are in there. Most of them are within 20% G, and then almost all of them within 10% G. This 10% G threshold, if you want to call it that, that's pretty well known that, you know, across the world, most coast-seismic landslides tend to happen within that contour. So it's they're really concentrated in this narrow zone along the fault rupture. The larger ones are more towards the northwest. And this was a unilateral rupture. So it started down here, ruptured up this way. And, you know, it was a little complicated up here, as Mike alluded to. But it started more strike slip and then kind of transitioned to a little bit more thrusting up here. So it's somewhat complicated. But yeah, it's interesting how well these kind of line up along that fault pattern. And so from the SAR mapping, we don't know what these mass movements are, and since it had recently snowed and it's winter, you know, many of them could be snow avalanches. And from SAR, at least with, you know, what we had available to us at the time, it was pretty hard to distinguish which ones were snow avalanches and which were landslides. So in fact, to give a preview of the upcoming story from the field reconnaissance, that area we were looking at in the GIF is in the red box here. Most of those are actually snow avalanches. So they're just really massive snow avalanches. And then most of the landslides that involved rock were actually in this area around Mount King George. So let's see. There we go. So we got our first optical image about a day after the SAR image came in. And so that actually confirmed, it showed this Mount King George area pretty well. And it confirmed that there were quite a few like mass movements that did involve rock, because you can see the dust coating lots of the area on the eastern side. You can see dust in here, and you can see darker colors incorporated into the flows. So it's probably a mix of rock and ice in some of these lobes. And the sunlight, the angle just really highlights these lobes coming out onto that nice flat glacier really nicely here. Okay, so we'll look closer at some of those events shortly in the photos from the reconnaissance flight. And so this is a map showing where the Yukon Geological Survey flew, and this was on December 12th, so just under a week after the earthquake happened. And they had beautiful weather and took some spectacular photos. But this is showing where they flew. They checked out all 3 of those main areas, but spent most of the time around Mount King George, because that's where most of the excitement happened. So the next couple of slides, I'm going to show photos. And so the Yukon Geological Survey made this nice map showing where these photos were taken and what angle they're looking at. So before each photo, I've kind of highlighted in green which area, like what our view is for the photo. And so just for reference, there's Mount King George again, and here's Mount Logan, here's MacArthur Peak. So we'll start by looking at this area that was around Mount King George. So we're looking from the southeast towards the peak. So this is one of the larger areas of ground failure, and we haven't done any quantitative estimates of volume. It looks enormous, this active rockfall scar, but comparing it to Google Earth, I think it's actually not quite as big as it looks. It's big, but I think it's thin, and probably a lot of this was rock fall. You can see there's no snow on this, no ice on this, so this whole face had fresh movement on it, and there was active rock fall happening when they flew by. You can see the arrow here. And given the really active aftershock sequence, and also the fact that when a big landslide happens, even if there aren't earthquakes, more material keeps coming down for quite a while. This is probably still, it was very active for a while and probably, maybe reducing a little bit, but probably still active now. You can also see the top of another scarp over here. We'll look at that in a few photos later. So this is the top of the longest run out landslide that we observed. And then you can also see this hanging glacier here. It looks very fresh at the end of it, so probably there were ice falls from this. And then you can see how sharp and fresh the edges look. So, probably a lot of material from along this ridge came down with some of these rock falls. Okay, now we'll look at the same area, but from the east. So where we were just looking is here in the background. Hopefully you can see my pointer. And you can see the valley is filled with dust still because of the active rock fall. There's quite, it looks small, but it's probably big, if this happened in California or here, quite big by standards further south. But this is a rock avalanche in the foreground, and you can see the pattern of dust it leaves across the glacier. And the glacier itself, a lot of the snow bridges collapsed from the shaking. And there's, everywhere you look, if you look closer, there's signs of rock falls and ice falls and snow avalanches, but these are really impressive here in the background. This is almost 1,700 meters of relief, and there's these two, I guess they're probably rock falls. I didn't measure the slope of this, but extremely steep falls of over 1,700 meters. So just really, really impressive stuff. Okay, now we'll look from the southeast towards the same area, and we'll see the longest run out landslide. And so you can see this started as rock. You can see how, it's freshly cutting into the rock. But from the color of the deposits, you can tell it really incorporated a lot of ice and snow as it flowed, and it went 7.4 kilometers and is almost 2 kilometers across. And so the presence of ice, flows going over ice and also incorporating ice and snow really kind of increases the mobility of landslides, and I'll talk about that in a little more detail later. And there's also, again, everywhere you look, lots of little failures like this smaller one that's kind of in a opposing direction coming in. And here along the ridge, there's a bunch of little rock falls, though they're probably not little by our standards. Okay, and then the next few slides over, I like this photo because it really highlights the structures and the flow. You can see these are longitudinal flow lines. I'll talk about those in a minute. This one over here, you could see it's composed more of a higher proportion of rock than some of these other ones. And that also plowed the snow and ice at the top of the glacier in front of it in a ridge here. This one kind of did as well. So now we'll look at the two other massifs briefly. So this one is around Mount Logan and MacArthur Peak. This is where that conjugate plane kind of goes through this area and a lot of aftershock activity. So this did have a couple of rock falls. You can see the patterns here. But most of the activity on this massif was snow avalanches or snow and ice avalanches. And these are huge, 1.5 kilometers across, 1.1 kilometers across. And so that, that first image we looked at with the SAR GIF before and after, a lot of those big footprints, those are just extremely massive snow and ice avalanches. Here's another really large avalanche on the kind of the north part of the Mount King George Massif. So this one went all the way across the valley, almost 2 kilometers, and then kind of up the other side a little bit. And then there's a lot of interesting response of the glaciers to the shaking, especially in the steeper tributary glaciers. So down on the Mount Vancouver Massif, this is showing a lot of basically almost every serac collapsed, lots of topples and falls of seracs. And you can see some signs of some detachments of ice and rock in the surrounding hills, but it's not quite as dense as we saw in the, especially in the Mount King George area. So the Yukon Geological Survey, they published a report, and in that report they had, using their field reconnaissance and some of the optical imagery, started to map where landslides occurred that actually involved rock. So those are these white dots here. And so their conclusion after their flight and after looking at the imagery more is that most of the activity was in this massif around Mount King George, and not so much, mostly snow avalanches in these other areas that were, if you remember, were highlighted by the ground failure product more prominently than Mount King George was. And so that's actually kind of an interesting thing we can look into to kind of understand how can the ground failure patterns inform us about where the fault's located and what the ground motions were. So Mike showed a similar plot. This is in that report that the Yukon Geological Survey published recently, showing an aftershock relocation. And so this blue line here is actually a plane fit to the aftershocks that were kind of on that connector fault, and then this line here is a plane fit to the aftershocks that were more in the conjugate fault area and had more reverse mechanisms. And so just as an experiment, and this is very qualitative and preliminary, I took that fault plane, which is actually shifted towards the northeast from the one that we have in the shake map currently. And remember, that one is based on the finite fault product, which is based on the hypocenter location and its strike and dip. So that's why it's down here. That fault is more below the glacier directly. This one is steeper and is actually more directly below Mount King George and puts that much of that massif on the hanging wall of the event. Though this was a complicated event, it was strike slip and oblique, so it's, well, we'll talk about that shortly. So there's a lot on this figure, but basically on the left, I'm just showing the landslide locations from the previous maps for reference. In the middle, this is the current shake map. And so these contours are the PGA contours. This magenta outline is the fault that is used by the shake map. Here's the epicenter location, and then underneath is the ground failure products probabilities for landslides. And so, as you remember, these two areas, they did have mass movements, but they were mostly snow avalanches. And actually where most activity was here, which is highlighted but not strongly. But if we shift the fault to the one from the that aftershock relocation, it shifts everything towards the northeast, and it does highlight that Mount King George area more strongly, and then it decreases the probabilities. They're still elevated, but decreases them in those two other areas. So it kind of better fits what we saw, or what the Yukon Geological Survey saw on the ground. And of course, this is a really complicated event. We could add the conjugate fault in there, and then it has a different mechanism, and maybe it's not just one conjugate fault, maybe it's multiple ones. So could get really complicated here, but kind of qualitatively, the overall patterns of the ground failure kind of support this northeast shift. And it's also interesting to think of this in the context of other earthquakes elsewhere in the world, such as California, obviously. And so kind of an overall finding from the literature after analyzing all the patterns of ground failure from many different earthquakes is that when you have a reverse fault, most of the landslide activity is on the hanging wall. And it also extends further away from the fault when you have reverse faulting than when you have strike slip faulting, where it's typically a pretty narrow zone of landslide activity right along the fault. And so the hanging wall effect, we know that's a really well-known reason for having increased ground motions, but also there could be a component of deformation of that block itself that also contributes to the triggering of landslides. Because we've seen, event after event, most of the really large landslides triggered by crustal earthquakes tend to be either right on the fault or extremely close to it. Just for context, I'll end with a quick comparison of some other events in the region and some, and I'll try to maybe relate it a little to what you might experience in California. So I'll start by highlighting some other events in, these two are in Alaska, that had very large rock avalanches onto glaciers. So at the left is a photo from the 1964 magnitude 9.2 Great Alaska earthquake, which was a subduction zone earthquake. So much larger and different mechanism, much longer durations of motion, much larger area shaken, but it did trigger quite a few very large rock avalanches. This one was originated up here. This is fresh snow because this was taken a little while after the earthquake. But you can see this looks similar. It has some of the same features as some of the ones we were looking at, just has a lot more debris in it than some of the ones we were looking at. And this is an example of, this is kind of a line of rock avalanches here along the Black Rapids Glacier that were triggered by the Denali earthquake. So that was on the same fault system as Mike showed, but further to the northwest and larger magnitude, but similar mechanism. It was also strike slip. And in this event, it triggered landslides pretty narrowly along the fault, narrower than people were expecting. A lot of the papers about this event talk about that, and it was a strike slip event, so that makes sense. And then it also caused more landslides in the area towards which the fault ruptured, and so there's a lot of discussion of directivity, and also part of the rupture behavior emitted more high frequency energy at that end as well. But you can see that these look a lot like the ones we were looking at for the Hubbard Glacier event. And so landslides onto glaciers tend to travel further and faster than landslides that are not onto glaciers. And part of that is because there's ice and snow that can melt and can add more water. It's also because there aren't as many barriers in the way. You have these nice open flat surfaces, especially on these massive glaciers in Alaska. And so it can just spread out more evenly and thin. And you can see this one went so fast, you know, it came from over here. It went so fast, it just went over this this medial moraine and then up the other side. So these can be very, very long run out and fast. And they tend to have these longitudinal flow bands like the stripiness and also debris tongues when there's any sort of minor barrier, because it's so flat and it encounters any sort of irregularity, it tends to break into these like finger-like tongues. And that causes these flow bands from differential motion and also tongues at the end, like you can see here. And then some other events that, well, the first one, the Anchorage earthquake, did not trigger landslides like we saw at Hubbard Glacier. So the Anchorage earthquake, similar magnitude, a little bit bigger, 7.1, but it was much deeper. And so the ground motions are less intense. A larger area might be shaken, but less intense and less focused. You know, like the Hubbard Glacier is very focused close to the fault. Here, the fault is not near the surface. And so for this event, a wide variety of ground failure was triggered over a pretty large area, but it was not as dramatic as Hubbard Glacier by any means. This is probably the largest landslide that was triggered, and it's, you know, compared to Hubbard Glacier, it's kind of underwhelming. And they just weren't concentrated in like a band like you see for this event. And then, of course, here's the famous Latoya Bay earthquake that caused the mega tsunami from a landslide falling into a fjord. So the tsunami had 530 meter tsunami run-up. I think the highest run-up ever measured for a historical tsunami, though a recent event in Tracy Arm got close. And so this is what can happen if an event like Hubbard Glacier happened closer to water, is that you change the hazards and you can get these large tsunamis, especially in Alaska, where they have a lot of these fjords. And so Bruce asked me to talk about lessons for California and whether landslides like we saw in Hubbard can happen in California. And I would say that California has a long history of landslides caused by earthquakes. And you could get landslides as large as the ones in Alaska, especially in the higher mountainous areas. But you don't have the same type of terrain. You don't have these big flat glaciers. So I think it would look pretty different from what we're seeing here. But A lot of the same rules apply in terms of the, the mechanism, if it's on the hanging wall or if it's close to a strike slip fault, that kind of changes the patterns you'd expect. And also of course, the depth of the earthquake matters a lot for the ground motions as well. So with that, I'll end by just leaving a few links if you want to read more about this event. The first link is the webpage that the USGS laser team made with the Yukon Geological Survey. And so those the field photos are in a viewer in there with some captions if you want to look at them closer, and including some that I didn't show today. They also wrote a guest blog entry for the landslide blog and added even more photos that I didn't show today. And then here's the link to the earthquake event page that I showed, and then the link to that report that I was showing material from towards the end. So with that, I will end.
Okay, Kate, thank you very much for a very informative presentation. The photographs were outstanding. The thing that really blew me away was the magnitude of the slides. The material that was moved and all that is quite amazing. Okay, I want to thank both Mike and Kate for their very informative presentations. Now I'm going to turn control over to Don to handle us for the Q&A. So Don, please proceed.
Thank you both, Kate and Michael, for your presentations. I really enjoyed them. It's really interesting to see the extent of the landslides. There was one brief question about which ground motions recording station reached 4% G, and Michael, maybe that's something you could take a whack at in the live blog, or unless you want to answer it off the cuff. Someone had been looking and hadn't found that yet.
I will tackle that in the chat.
Okay. The other questions are a little broader interest from one of our colleagues at the U.S. Geological Survey. Tom Brocher is asking about the thickness of the avalanches, and the thickness of the larger avalanches, what those might have looked like, both the landslides and the avalanches.
Yeah, it's hard. We haven't done any quantitative assessments yet. And it's hard to get a sense of scale in those photos. Everything's just so big in Alaska. And I don't think that they touched down on the helicopter. I haven't seen any photos from the ground. So I'd say we probably don't know. Some of them look quite thin, like maybe just a meter or two, and some of them, especially the ones with rock in them, are probably a little thicker, but like maybe 10 meters or tens of meters. I don't know. It's something that we haven't really measured yet, but these landslides onto glaciers can be extremely thin, as you saw, especially in that Denali photo, because they just spread out so much.
With the flow lines, they must have some thickness, though, if they're forming those, I would think.
Yeah.
I'm used to seeing landslides which sort of liquefy and go down a hill with water in them. Are you melting the snow quickly enough that it gives fluid to these things that allow them to flow across the glaciers like that?
Yeah, that's there's quite a few papers that try to model why landslides onto glaciers are more mobile, and most of them invoke that melting. When you have debris with ice, especially the friction from that can cause melting. And so that's one of the theories for why they run out further, is that it kind of decreases the effective friction angles. Yeah.
I was trying to look in Google Earth, and Tom also asked, was there any surface rupture? I can't get my
No,
Google
that
Earth
was
to
a
work
big,
to look to see if where the fault is compared to the
yeah,
glaciers.
that was a big goal of the recon, and also the remote sensing. We were all, between the USGS and Yukon Geological Survey, trying to figure out can we figure out where the fault is? And the Denali earthquake actually did rupture through glaciers, because it's kind of a question, like, if it ruptures to the surface, like, will it keep going through the glacier? And at least in Denali it did. So it was reasonable to expect that it could rupture the surface of these glaciers.
What?
But it could be, given that the evidence suggests the fault is more under the Mount King George Massif, that the fault actually goes through there instead of directly under the glacier. But I think that'll be probably the topic of a lot of future investigations. Yeah.
Yeah, maybe model more INSAR imagery or things like that too, but to
Well,
see what the
yeah, the
ground
INSAR
deformation
INSAR
is.
did not work because of the
Yeah.
snow and the
Yeah.
yeah.
Mm,
So
okay.
traditional INSAR did not work. It was tried, but and no, they did not see any sign of surface rupture in the reconnaissance.
Yeah, the finite fault model is, of course, showing quite a bit, upwards of 1 to 2 meters of slip near the ground surface. So it certainly could be expected that there would have been, but it may in fact have been buried then, or maybe let's just say hard to find. Um, uh, One other just some comments from Jet Rubin and others noting someone was asking about whether there might be maps showing predictions of landslides from a subduction event in Alaska, and I think Michael answered that and said there really wasn't anything like that.
Yeah, I mean, we do have, if you go to the webpage for the 1964 Great Alaska Earthquake, we did run the ground failure product for that, so you can see what that product looks like. And then we also recently released a digitized version of all the ground failure that was mapped from the 1964 earthquake.
Oh, okay.
So, there's a series of reports from a few years after
Yeah.
the earthquake. And so Sonia Ellison spent several years, not just doing that, but it took several years to kind of go through and digitize everything that was mapped. And so now that's available
Oh,
electronically too. So,
that's nice to know. I'll have
Oh,
to take a look.
okay,
Yeah.
excuse me.
All right.
Excuse me, this is Bruce Mason. It's about 1 o'clock now. So Don, we could carry over, I'd say, for maybe about 10 minutes on the Q&A. So please continue.
I think that that covered, most of the questions. There's some comments in the chat, about the concerns over large areas of landsliding from subduction events, both for the Cascadia subduction zone as well as the Aleutian subduction zone. And
yeah,
so,
we also can run scenarios. We've run a few, I think we've run Cascadia scenarios too, but the ground failure models, both the landslide and the liquefaction ones, they're very coarse models. It's just kind of a way to get a sense for where to expect it. And then, but it's not quantitatively good at predicting the actual locations or the actual area. It's just kind of like a way to get like the blobs where stuff probably happened.
right. Yeah. All right. Uh, Any quake lakes anticipated this coming summer? Meaning, I guess meaning areas where water would be trapped by landslides? Is that what
Um,
you meant, Charlie?
I
Such
I
as
don't,
Hebden Lake,
none of
where
the ones that
uh,
I looked at, like when we were doing the remote sensing, seemed like they were damming rivers. Most of these are going out onto glaciers, so I don't recall seeing any, but we didn't look everywhere. We didn't look like that far beyond um, the map that was shown. So it's always possible there's something that we didn't see or something that was smaller or didn't show up well on the SAR, and they didn't fly everywhere. The Park Service was going to fly too, but in the U.S. side, but they didn't manage. They weren't able to. I don't know exactly why. Um, so so there could be things that happen that we don't know about, but my guess is probably not.
okay. Well, thank you very much for all that information, both Michael and Kate. Bruce, did you have any other questions? I
Oh,
don't see
I
any
got
other
perhaps one
questions
final question, and this is for Mike.
in the chat.
I like asking the seismologist. It seems like when we have earthquakes in California, they're always surprised. Was there any surprises from this event that you had in
Pleasantly
Alaska?
surprised.
And if you could just speculate as to what they might be.
I mean, I can comment generally that I agree with you entirely, that the next earthquake almost always seems like a surprise and not necessarily the one that we're expecting. I mean, this one was again, that's kind of why I dwelt on the tectonic background a bit, because this one there's it feels like it felt like it was supposed to exist, but there really hadn't been signs of it before. And for all the reasons, Kate pointed out with the photos and whatnot, there's no, it's not a place where you go out and just map, the historical motion on the fault. Like It doesn't have that, or we haven't found it yet. So that's the surprise.
Okay, good. Thank you. Anything else, Don, or should we wrap it up?
Nothing else. Thank you again for our speakers.
Okay,
I'd like
Don,
to
do you have any
thank our
comments?
speakers. I'd like to thank our speakers today. Before I turn it over to Maggie, just one comment. I think it really underscores the hazards presented by the San Andreas system, the west coast of the continental United States, Canada, and Alaska. And most people and decision makers don't realize how they're linked together. So this really illustrated that risk, that hazard, that risk presented by that hazard. So thanks to our speakers, and Maggie, I'll let you close it out.
Thanks everyone, and thanks everyone for joining. Just a few final reminders. Please complete the post-webinar survey that will pop on your screen after we end this webinar. There'll be a follow-up email that you'll receive tomorrow, excuse me, with more information about PDH and more information about EERI. And we'd just like to thank FEMA one more time for their support in helping make these webinars happen. So thank you, everyone.
Okay, bye-bye.